Good evening. I'm Samuel Sivy, Délégué Général of Institut des Actuaires and one of the coordinators of the Young Actuary Initiative. And I'm delighted to welcome you to this new webinar from the French chapter of the Young Actuary Initiative. This evening, Michel Vujigena, Associate Lecturer at University of New South Wales in Sydney, will present a thesis modeling mortality heterogeneity in longevity risk applications using health trajectories and multimorbidity, work for which she was awarded the 2024 SCORE Actuarial Prize in Asia Pacific. Michel, thank you for being with us at such an hour, 2 a.m. As usual, you all will be able to ask your questions through the chat, and Michel will answer at the end of the webinar. Michel, the floor is yours.
Thank you very much, Samuel. So as Samuel said, this is joint work with my supervisors, Professor Michael Sheris from University of New South Wales, Sydney, Associate Professor Andres Villegas, and Associate Professor Jonathan Zive, also from the University of New South Wales Business School. So I'll start off with the outline of my presentation today. I will go through introduction briefly, talk to you about the data, discuss some of the methods we used, and then I'll finish off with a discussion of some of the results and conclusion. I'll be focusing mainly on the last chapter 5 of my thesis, which is the chapter that I remember the most. I'm still working on publishing this paper. So the background, we know that there is a huge demand for long-term care, and this is expected to increase globally in the next few years. And across OECD countries, we know that more than 50% of individuals age 65 and above are expected to need long-term care. And in terms of costs, this public spending on long-term care ranges between 0.5% to 4% of GDP of most OECD countries. So private markets also have an opportunity here to offer long-term care insurance products in the form of traditional insurance or life annuities combined with long-term care, popularly known as life care annuities. So our goal is to kind of have an increase in the product offering, to kind of increase the demand of long-term care products, particularly from the private markets. So how we want to do this is by making sure that we're pricing mortality risks and functional disability risk accurately. And what we've noticed in the literature is that there's an omission of um, a popular phenomenon known as multimorbidity, which is the presence of two or more diseases with or without impairment. And in the epidemiological literature or in the public health literature, multimorbidity is very widely researched, but as actuaries, most actuaries don't incorporate this information, even though uh, a lot of the aging population has multimorbidity. So how is it defined? The first way is the easiest way, which is as using the number of diseases, which is two or more diseases. And this was discovered in a study, in a literature review study by Merengoni et al. In 2012. But there, as you might be aware of, there are other approaches of defining multimorbidity, and one is to use an indexation approach. This has been noted in the literature, particularly by Charlson et al., Greenfield et al., and Imamura et al. In 1997. But what does the indexation approach actually mean? In this case, you actually have a reference disease. Say you look at diabetes as your reference disease, and then you look at how other diseases are add on from this reference that you're looking at. The disadvantages of using such a definition is that usually it needs clinical expertise. Um, and the data that is usually accessible doesn't usually give us the timing of each disease that an individual has. Another way of defining multimorbidity is looking at the pool of diseases. And what this means is that if you have a data set and they have um, different diseases, you must make sure that the pool of diseases that you're looking at covers at least 12 conditions. What this does, it reduces bias in your estimates of the prevalence. And one disadvantage of considering this definition using the pool of diseases is that most of the data sets that are publicly accessible do not have more than 12 or more than 8 diseases, as we'll discuss later. Um, in terms of prevalence, there have been some studies that have looked at that have forecasted the like how much how what proportion of the people who have multimorbidity, and using a UK data set, Kingston et al., they show that more than half of the older population in the UK will have multimorbidity from 2015 to 2035. And in terms of risk factors, we know that generally being older, being a female, and having a low socioeconomic status is usually associated with multimorbidity. In terms of the actuarial literature, there's a paper by Sheris and Way in 2021, and in this paper, they propose a 5 health status and disability model, but they do not consider multimorbidity. In terms of multi-state models, I would say this is probably the most high-ranking and most commonly used model in the academic literature as far as incorporating health status and disability. Um, there are also other models which are simpler. These are the 3-state models of health and functional disability. And what this means is that you have a health state, you have a functionally disabled state, and you have a absorbent state, which is the dead state. And in this 3-state models, they do not distinguish between multimorbid and healthy individuals, which is an important aspect of why I carried out this research, because what we're seeing is that the multimorbid individual is being treated the same way as a health individual, which is not allowing us to price risk accurately. And if we go back to the general epidemiological literature or public health literature, we find that there are a lot of multi-state models that are being used, and they're being used to calculate mortality rates, incidence rates, and prevalence rates of multimorbidity for both men and women. However, because I guess because they are not using an actuarial lens, they don't consider functional disability or recovery from multiple morbidity. Functional disability, I'll define a little bit later. So just to make sure we're all on the same page. But it's essentially the uh, inability to perform activities of daily living. So we see that the main gap is that there is no link in the literature that's between multimorbidity and the pricing of long-term care products. So we have this quote from Richard Thaler, who won the Nobel Prize in 2017, and he talked about how um, while accumulation is easy, it's an easier problem to solve in as far as retirement planning is concerned, because you're just focusing on maximizing returns. It is decumulation, which is how do you decide how much to take out of this lump sum that you've accumulated during your working life. It's very difficult. And as actuaries, we have a role in designing and pricing this fair and sustainable decumulation products. So using that economic lens, we want to see how can we then incorporate multi-morbidity in actuarial pricing. So because my research was funded by a sustainable development grant, I have to tell you upfront before we talk about the data and methodology and results, how this research is related to the sustainable development goals. So the first SDG where this research covers is SDG 1, which is no poverty. And we want to make sure we end poverty in all its forms, particularly in our research through maintaining a sustainable income during one's retirement life. We also want to reduce inequality within among countries, and how we do this is by making sure that we focus on on ensuring that all risk classes are able to um, get the annuities or long-term care that they need at a fair price. One thing I could also just clarify here is that what we see most of the time in annuities is that they're usually very expensive, particularly for individuals with very low chances of having a high life expectancy. So we want to make sure that whenever we create these financial products, we take that into account and make sure our products are equitable. So now for the research questions. I have three. The first one is, what is the impact of multimorbidity on transition rates in a model of health and status and functional disability? And we also want to, because we're going to use two models, a 3-state model and a 5-state model. We want to see how effective a 5-state model captures the differences in mortality and functional disability risk. And the third one is, what are the pricing implications for the incorporation of multimorbidity into longevity-linked products? So the data we're going to use, or which I used in this project, is the Health and Retirement Study data set. And this is a study that's run by the University of Health and University of Michigan, and it follows Americans age 50 and above. It was started in 1992, which is the earliest wave, and uh, the data is captured biennially, which is once every 2 years. So for our purposes, we use the waves 4 to 13 because these have more consistent uh, definitions of activities of daily living. And they are the ones that are focused on by literature that looks at functional disability and mortality risks using longitudinal individual level data. So when I say that the data is longitudinal and individual level, it means that for every individual, we're able to capture economic, demographic, and even genetic data information about an individual. Some data are restricted, such as genetic data. But information about people's social security, how much their house costs, um, um, where they live, or um, what proportion of their income or wealth is in shares, in equities or property. All that information is available. So how do we clean this data set? So we exclude, for our purposes, we exclude people who do not provide, who 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 fail to provide correct responses, like uh, if something is uh, like maybe the date of death is great is earlier than the date of birth. Obviously, that is bad data, and we throw that away. But we also look at who is failing to respond in any wave, and we say if you're not appearing in consecutive waves, we throw out your data so that we have a consistent data set. We define multimorbidity as the presence of more than one chronic conditions from the following diagnosed conditions. And I just want to point out that these doctor diagnosed conditions are self-declared by the individuals. So we have high blood pressure, diabetes, cancer, lung disease, heart problems, stroke, psychiatric problems, and arthritis. So that's 8 conditions. And in terms of activities of daily living, there are 6 activities of daily living. So functional disability is defined when an individual fails to perform 2 or more activities of daily living. So if you were pricing a long-term care contract, you would see that if anyone fails to eat, is failing to uh, take a bath, is failing to dress themselves, is failing to transfer like from one position to another, or going to the toilet, or just basically walking or moving around. If any 2 of these activities are not, they are not able to perform this, if they have purchased a long-term care insurance policy, you would have to start uh, paying out their claims. So, what is the three-state disability health and disability model? So it has 3 states. The first one is the healthy state. The second one is the functionally disabled state, and the last state is the dead state. And there are 4 transition types. So if you want to go from the healthy state to the dead state, you describe that transition type as S is equals to 3 on the chart there. And what's important about this functional disability model is that we allow recovery from functional disability to the healthy state. And then we also consider a 5-state multi-morbidity and functional disability model. And here in addition to the healthy state and the functionally disabled state and the dead state, we add 2 more states, which is state 3 here, which is the multi-morbid state and not functionally disabled state. And we also add the 4th state here, which is the multi-morbid state and functionally disabled state. And you can see here that there are now 12 transition types. We're not in this diagram, we don't count the occupancy probabilities here. They are not numbered. We just showed them here using this arrow that turns on itself. So if you're looking at the healthy state, which is state one, we can see that there are actually four ways to leave this state. You can move, let's say, from the healthy state to the functionally disabled state. You can move from the healthy state to the um, m- morbid state. Uh, I'll just, or you can move here. So, and you can also uh, die. So this is so what this diagram is just doing is just telling us what the states are and showing us how an individual might transition through these five states. So now that we know the three-state model, and we have proposed this five-state health functionally disabled state with a multimorbidity state two, how do we then extend the three-state models? So we use a proportional hazard specification, and this is similar to what's done in Lee Shao and Sherries in 2017 and Sherries and Wei in 2020. And what I'll just wrap this out first, these arrows. Yep, thanks. So um we model the transition intensity using S, and this goes from 1 up to up to capital letter S. And for the three-state model, the S is just 4 transitions, and for the five-state model, it's 12 transition types, as we saw earlier. And here this shows the how we model the transition intensity, and I will just describe the parameters so that we are all on this same page. So beta S here is the time invariant baseline log intensity for the transition type S, and WKT here is a vector of the observed predictors. So in the case of the health and retirement study, if you, let's say, are interested in BMI, that would be a predictor, and it would be captured in this vector W. And then we also have psi t here, which is the frailty, and this captures the uncertainty, and this is a stochastic latent process. And um, we also have this color indicator variable, which is equal to 1. Um, so this allows us to make sure that we don't account for transitions that are impossible. So this makes sure, let's say, if you are in the dead state, there's no way you're going to recover, let's say, to the healthy state or to the functionally disabled state or to the multimorbid and functionally disabled because you're dead. So it captures all that, all those dynamics. Um, so we look at there are actually uh, 3 ways we could nicely write out this models, and we introduce what we call a static model. So where a static model here, we are looking at probably just 2 or 3 predictors, and we are not incorporating the trend or time. So in this case, we would have a model where we have the age covariate and its coefficient. We have the sex or gender variable, and we have the multimorbidity status, which is a 1 or 0. And the the sex here is the sex assigned at birth. Um, and the different coefficients here are, they measure the sensitivity of the log transition rate with respect to age, with respect to the female variable, and with respect to the multimorbidity. It will, if don't get too worried about this equation. You'll see how it looks like when we talk more about the results. If we wanted now to capture the effect of time, we would have to add a time trend. And how we do this is by adding this variable phi is time t here, where phi is measuring the sensitivity of the log of the transition rate to the time trend. And we also have what you find is probably the best model, which is a frailty model, which captures both the systematic trend and uncertainty. So the frailty model is dealing with the limitations of the Cox proportional hazard model. So that's how we make this models more robust. So if we then have fit our data and we wanted to see how exactly uh, uh, this model, whether this model is a good fit or not. And here you can see the raw data here, let's say for transitions from the healthy state to the disabled state in the first panel here. You will see that sometimes our model underestimates or overestimates the transition intensities, but it's basically a good enough fit, except for the higher ages where we have scanty data. If you look at the region from 105 to 110, there's basically nothing here. And as some of the what we can see here makes sense already, which is that females, let's say we look at mortality rates, um, females who are not multimorbid would probably have lower transition intensities than females who are multimorbid. Um, so that's the way, in terms of probability, if probabilities are easier to understand, you would say that males have higher probabilities of death than females, which is kind of a reasonability check that you could test out that you could test when you're looking at the different transitions from healthy to disabled, from disabled to healthy, and from healthy to dead, or from disabled to dead. So now let's talk about some of the parameters that we're able to get. So how do I explain this table? So we have our transition types, which are healthy to functionally disabled. That's transition type 1. Here we're focusing on the three-state model. In transition type 2 is from that functionally disabled state to the healthy state, and so on and so on. And then we on the first column, we identify the parameters that we're interested with. We get we note the values for beta. Uh, we note the um, we note the parameters for age, for female status, and for multimorbidity. So if I, let's say, look at the column for column 3, which is state the transition uh, type S is equals to 3, which is the probability that people are moving from healthy state to the dead state. We see that as age increases, this transition is increases, right? The likelihood of this happening increases. And if you're a female, it's less likely that you will die compared to a male. And then we see that people who are multimorbid are more likely to die uh, from the healthy state. And uh, this effect is not seen when we look at, let's say, the transition from the functionally disabled state to uh, the healthy state. We see that the coefficient there is negative, meaning that people who are multimorbid are less likely to recover uh, to the healthy state. So we should also do this again for a time trend model. Here, on the last row here, we capture the effect of time. And we do this also for the five-state model. So I'm just going to summarize what these parameters mean if, let's say, we consider the five-state model. In my thesis, you would see more of these tables, which are very long. Um, but just for the purposes of this presentation, I will just summarize. We see that if you're moving from the uh, let's start with the first bullet point here, which is we see that mortality rates increase with age, and this is not a dramatic result because that's what we would expect. Um, and we see this effect from the healthy state to the disabled state, from the multimorbid state to the disabled state, from the healthy state to the dead state, from a multimorbid to the dead state, functionally disabled state to the dead state, and from the multimorbid and functionally disabled state to the dead state. And we also see that disability rates increase with age. So here we would be looking at these uh, transitions. This is from healthy to functionally disabled, or healthy to multimorbid and functionally disabled, and so on. And what we introduce, that's probably something that's not in the literature, is how multimorbidity rates from the health state increase with age. And this col uh, cor corroborates the evidence that we've seen in the uh, previous literature I discussed in the public health and epidemiology literature, where um, and we see this in effect in these two transition types. And we also see that multimorbidity from the functionally disabled state decreases with age. And we also see that recovery rates from functionally disabled state decrease with age. So these are how you would interpret uh, how this model um, uh, how this model fits the age predictor. Okay, so if we consider now females, the gender aspect, we see that females have lower mortality rates and are more likely to become disabled than males. We also see that females are more likely to become multimorbid and functionally disabled than males, which is correct. And females are less likely to become multimorbid than males. And again, how we get this, we'll look at the table of the results and look at these transition types, healthy to multimorbid and healthy to multimorbid and functionally disabled. Now, we can also then, because of this methodology, we can establish the multi-year transition probabilities for the healthy state and functionally disabled state. Here, I've shown the multi-year transition probabilities for males at age 65 using a static model just for simplicity. So, Or when I say static, remember that means we're not showing, we don't have a trend predictor. So uh, if someone's interested in what do these probabilities mean, we would say what TP65 is this first one. That's the occupancy probability, right? At age 65 and time 65 plus T, right? And the second one will be your multi-year transition probability from the healthy state to the functionally disabled state, and so on and so on. And we do this for the healthy state, and on the right you can see this results from the functionally disabled state. And everything, if you wanted to do a reasonability test, everything seems to make sense. Occupancy probabilities are decreasing as time goes, and the probability of one becoming functionally disabled, it increases, then decreases. Yep. So you can do this again for the multimorbid state where you again look at the multi-year transition probabilities for different transition types, and you also always consider um, the occupancy probability. And if there's a recovery, like here, this is like if from someone can go from state 4 to 3, and they can go from 3 to 4. So if you've got the reverse, it means there's a recovery that we're taking into account there. Uh, um, we also have the multi-year transition probabilities for the dead state, and if you remember, state 4 is the multimorbid and functionally disabled state, and that has the highest probabilities over the duration we're looking at. Um, and then based on this, we are able then to estimate life expectancy statistics. We're able to um, show the different life expectancy result for the whole group, and for the multimorbid group separately, and the individuals who are not multimorbid, but by their gender. If they are female, we see that females who are not multimorbid tend to live the longest. And according to this to our model, if a female age 65 who is not multimorbid is expected to live for an extra 25.45 years. And a male has 3 years, lives almost 3 years less. Um, in terms of when they become disabled, we see that you would be looking at the age at onset of disability, conditional on that they become disabled. And what we see is that people who are not multimorbid generally um, have a later onset of disability than people who are multimorbid, or if you just group them all, they still have the highest age at onset. And in terms of the proportion of healthy life expectancy, we see that um, um, females and males who are not multimorbid have the highest healthy life expectancy over life expectancy, around 90% for females and 93% for males. So and then in terms of disabled life expectancy, we see that this multimorbid group, they have um, they have spent a long time being disabled, and they also have the shortest uh, healthy life expectancy. So, just to summarize our findings, the five-state model shows the differences in life expectancy of both and it's able to capture the dynamics of how multimorbidity and disability evolve over time. Uh, if you are using a predictor as shown in the three-state model, you tend to overestimate life and health, life expectancy, and this has a significant impact for pricing annuities or other longevity-linked products. We also see that healthy life expectancy is overestimated in the three-state models, and individuals seem to spend more time multiple morbid than disabled. Okay, now here I show a comparison of the premiums for insurance products using the three-state model and the five-state model. And how we're doing this is we're comparing the healthy state in the three-state model with the healthy state in the five-state model and the multimorbid and not functionally disabled state. So here I only show the results of the static model and the trend model. And what we see is that for a life annuity, for males, if we use the healthy model, healthy, if we look at the healthy individual, we'll see that premiums should be probably 15.18% higher than what we're charging. And if we look at an individual who is multimorbid and not functionally disabled, and we estimate how much their life annuity would cost, we see that it would slightly cost more in uh, the five-state model than it would in the three-state model. We do this again for long-term care, and we see that for the multimorbid and non-functionally disabled individual, the premiums for their policies could be 28% higher, or for females, even going up to 30%. So, if you then do a combo product and you have a life annuity and a long-term care insurance product bundled into one, we see that the premiums would be around 14% for male, 14.76% for males, and 10% higher. So in essence, what this is showing, if you look at let's say the life annuity, what we're saying is that because there's a slight difference here between the multimorbid and non-functionally disabled person and the healthy individual in the three-state, what our results are showing is that we're in the three-state model, we're probably pricing for this multimorbid and not functionally disabled person. That person we're not pricing for the actually healthy person, which is the healthy person. The truly healthy person is the one who is not multimorbid and not functionally disabled. So, what are our contributions? So, in this uh, uh, chapter of my thesis, what we do is extend the literature on multiple health state modeling by comparing two methods of integrating multimorbidity and health state modeling. We develop a five-state model that incorporates multimorbidity and functional disability with recovery, and it captures differences in the disability onset, morbidity onset, healthy life expectancy, and future life expectancy. With the three-state model, our contribution is that we extend this model by quantifying the impact of multimorbidity on transition rates. And lastly, we capture the effects of these differences in the pricing of um, life annuities, life care annuities, and long-term K insurance for both morbid and non-morbid groups. More details are in my thesis. If you want to take a look at that. But in terms of weaknesses, as you saw earlier in our exploratory modeling, we have a small sample size. This is just I think 31,000 individuals, but I think over 300,000 unique observations. And we in our future work, we would want to price for long-term care and um, annuities using the frailty model. And we also want to compare different life expectancy statistics uh, using the static model, the trend model, and the uncertainty model, particularly for the five-state model. I also want to acknowledge the Center of Excellence um, in Australia at the UNSW Sydney and for funding this research. And I also had to use a computational cluster at UNSW to fit this model because if you try to fit this model on your computer, it would crash unless you're just fitting the static and trend results where the trend models, which uh, in which case your results would be very quick, just a couple of minutes. And the rest are references. Thank you for listening.
Yes, okay, I think we're going to stop here. So thank you very much for this enlightening presentation. Thank you again for staying up so late for us.
Okay.
And yeah, see you soon and well done.
Thank you very much.
Thank you. Bye.
Bye.